Hi everyone, hope you're all doing well. In this video, I want to show you how you can derive the least squares estimates in the case of linear regression. I've already shown in a previous video in the series how you can do that using the techniques of linear algebra, which I think is probably the more important thing to learn for people that are just getting their feet wet with higher levels of statistics. But I do want to show how some of the techniques of multivariable calculus can also be useful, even though linear algebra is maybe a higher priority just because it's so naturally the language of statistics. So what we want to do here is find some, and we're just going to focus in this video on the case of bivariate regression. So find some beta naught, which is the intercept, and we can write these with tildes here, and beta 1 to minimize. And what are we trying to minimize here? We're going to minimize the sum of squared residuals. And there are some reasons that we don't need to worry about here why we deal with the sum of squared residuals, but hopefully it's intuitive that we should try to minimize some function that involves the residuals, right? So how do we write that? Well, let's write out a loss function here. So we'll say that the loss function associated with beta naught and beta 1 is equal to, so we're going to write out the residual here. So we'll say, let's write this out like here, and I'm going to use E to refer to the residuals, even though that's somewhat confusing to be completely honest. But many textbooks, including the one that I'm using as my sort of source material for this set of videos, Wicken's Geometry of Multivariate Statistics does use it, even though he's pretty careful to distinguish between residuals and errors, and that's the reason why this E here might be a little confusing. Pardon me. So what we want to do is now figure out how to write that residual vector in terms of beta naught and beta 1. And by the way, notice that this notation here means sum of squared residuals. And the reason for that is that we have here what these bars indicate is these indicate the length of a vector. And remember that the length of a vector v is simply an extension of the Pythagorean theorem. So it's equal to v1 squared plus v2 squared, etc. So when we then have the squared length, we just eliminate, I'll do this here, we just eliminate this here, and so that ends up being the sum of squares. Okay, so then what's our next step? It's to write this out in terms of the actual coefficients here and the variables. So we're going to say we want here y minus beta naught minus beta 1 x1. And now what we want to do is take the derivative of this thing, and I'll show in a later video how you can do this with a little bit of simple matrix calculus, but I want to show in this video that you don't really necessarily need those techniques. So let's do this sequentially, and let's write out just what this is, but using basically the techniques of scalar calculus. So we're going to find the derivative of this function here. And we do have two variables in here, but let's just focus first on beta naught. So what is this equal to? This is equal to and here I'm just going to eliminate the subscript here on the x1 to avoid excess notation. So we're going to, because we only have one predictor, one x here, we're just going to say xi here. So we're going to write it out like this. And then what we want to do is set that equal to 0. And by the way, this should be a question mark because we haven't actually written out the derivative yet, but I just wanted to show you that you can write it out in this convenient way. So in a previous video in this series, I showed you that you don't need to be scared of this sort of fact that we've got basically this summation term in here because the addition rule from single variable calculus tells us that we can basically just write out the summation and then take the derivative of all of the individual components. So let's do that here. So that means that we're going to write out like this. So we're just going to take all these pieces here. And what will we do to the individual pieces? Well, we're first going to pull down, according to the chain rule, at 2. And then we're going to take the derivative of the inside with respect to, in this case, beta naught. So that just becomes a -1. And then we do the same thing ahead. And then what we can do is set this equal to 0. And then the next step that we want to take is simply to divide this bit here and this bit here out. And this ends up becoming something very, very convenient. So we have this here. And then you can see that we're just going to do that sum right over again, right? So then we're going to sum up yi here. And we may want to go ahead and just write this out like this. So we're going to sum up beta naught. And we're going to sum up beta 1 xi like this. Then if we do all that out, so this component here just becomes n times y bar. So in this case, beta naught is a variable term, so we're just going to treat it like an x, basically. So this just then also becomes n times beta naught. And then here we can pull out this beta 1 from the outside of this last term here, and then just write this out. So this is the sum of the xi's. This is n x bar. That's all equal to 0. And then what happens in this case? Well, let's move over to the beta naught. Okay, so now we've got an n in every term. So we're going to cancel that. And what do we get in the end? We get beta naught is equal to y bar minus beta 1 x bar. So that's a pretty simple proof. And we can see that that gives us a nice sense for what the intercept should be. And doing this sequentially in this fashion is a really nice way to solve certain problems, even though we'll see later on that there's a way to sort of expedite this process. So what's our next step then? Well, now we want to take that same derivative of the function, but now with respect to beta 1. Sorry folks, so the video actually just cut off, unfortunately, right as I got to the derivative of the function now with respect to beta 1, which is fairly frustrating, but we're not going to worry about it. So let's go ahead and now try to solve for that. So we've got our least squares function here of beta naught and beta 1, and we're going to write it out like this. We're going to say that it's the summation of I equals 1 to n of yi minus beta naught minus beta 1 xi squared. And now we're just going to apply that same chain rule that we did before. And what we're going to do here is just apply it first without really thinking about the summation, and then we'll take the summation at the end. So we'll kind of write this question mark equals here, and we'll just put this ellipsis to indicate that we're aware that we're going to have some issues that we're going to come back to. But we apply the chain rule, and we do it like this. Then we just take the derivative of the inside, which is the derivative with respect to beta 1, which is going to be equal to negative xi. And then we say we're going to add some stuff here. And then what we want to do is just think, well, first of all, we want to set this equal to 0. And what that tells us then is that we can just divide out by this 2 here and this -1. And we can rewrite it as follows. We can say that 0 is equal to, and we can just put that summation back in here now. So it's the summation y equals 1 to n over yi, and let's multiply through by that xi now. Oops, there should be a 1, not an I. Like this, and this should be squared, by the way. Oh, sorry, no, it shouldn't. Take it again. And we get the following. So now let's go ahead and pass through that summation operator. And I'm going to stop writing out the indices here as I often do, just because it becomes a waste of time in a certain respect. So we pass through that summation operator here, and we do the same thing here. Now let's go ahead and write out what that beta naught is equal to, since we found it from before. And let's start doing some copying and pasting here, since that is the purpose of using this iPad. Okay. Then what's our next step here? Well, it's to go ahead and multiply through down here. Just copy this whole thing down. And we're going to multiply through. So when we multiply through, we get the following. That. And now we're getting pretty close to coming up to our solution. And let's actually move this over here. And while we're at it, let's pull out this beta 1 like this, like that, since we were allowed to do that, of course. And we can actually do the same thing here in the middle, but we'll do that in a second. So let's copy this down, but then again, continue making some kind of simple modifications. There's a lot of tedious algebra in this way of solving it, I have to admit, but it's kind of fun. So what can we do to this term right here? Well, we can actually pull out the y bar, and then it's just a sum over xi. And then what that becomes is simply the summation over n times x bar y bar. So we'll do that now. Or it's actually just n times x bar y bar. I think I said the summation there. And then if we think about what's happening here, well, we can pull out that beta 1 and pull out that x bar, and then it just becomes beta 1 times x bar times n times x bar. Let's cut this here. And then we don't really need to do anything with this term right away. So now let's go ahead and rewrite this again. Let's rewrite this out because this part's going to be fairly different. Okay, so now what's our next step? Let's move over that beta 1. And let's actually use the copy function here. Oh. All over the place here. Not exactly the most dexterous person, which is a reason that I teach math, is you're allowed to have terrible handwriting. Okay, so now we can actually just do a clever thing and get rid of that negative side on the left-hand side by passing it through. So we'll just do this. And now we can finally do one last clever trick here. Well, not quite the last one. So this might seem somewhat uninspiring because it seems like we haven't really done very much here, but it turns out that this is actually a really powerful formula for two reasons. So let's start by first writing out the formula for the sample variance, which is this. And hopefully you know this by heart, but we'll see that it has a nice transformation here in a second. So what if we now go ahead and expand what's inside of the summation there? So we can just do it like this. And then we've got, so minus xi x bar, there's a 2 in front of that, and then plus x bar squared. And we'll just write this here to conserve some space. And then if we pass through that summation operator once again, we have the sum over xi squared. And then we've got here, again, we can pull out that -2 in the x bar, and we just get this. So we say -2 x bar, and the sum over xi is just n times x bar. Then we have the sum over x bar squared, which is just going to be n x bar over n minus 1. And then what we can do is just finally, or sorry, we don't need to put those parentheses there, pardon me. We can just go ahead and gather up like terms here, and notice that these actually are going to come together, and we have a lot of like terms, in fact. So we just get this. We say xi squared minus n times x bar squared over n minus 1. And you might be kind of salivating over the fact that this is almost the same as this, but we don't need to worry about that because we'll get rid of that pesky term in a moment. The main thing to note is that the numerator here looks a lot like the denominator here. But let's go ahead and now rewrite these sample covariants in a also kind of useful way. I'll use this notation here. Okay, and we're going to again do that multiplication out. Okay, so let's go ahead and think about how we would sum this up. So this just becomes n y bar x bar. And the same happens here, just in a different way, but we get that x bar out of the summation times n, and then we just have y bar. And then finally, if we do a little bit of commutation there, we just get the same thing here. So except there's a plus in front of it. So n times x bar, y bar. And then this is all over n minus 1, even though it's a little tedious to write it out. And so finally we can rewrite that like this. Then we simply have minus n times x bar, y bar, like this. And then notice that if we come back up here, it's actually the numerator here. So let's copy this down. So this equals this. And then if we come back up here, we can see that this, oops, sorry about that, equals this. And we don't need to worry about the n minus 1s because they cancel. So that's a really nice fact. So then finally, if we come back together, we can say that beta 1 is equal to the covariance of x and y over the variance of x. And you might also worry a little bit too about the fact that this doesn't maybe look exactly like you've seen the sample regression slope for bivariate regression look before. But here's this nice fact. Notice the following. So r is equal to the covariance of x and y over sx sy. And it looks a lot like this formula here, except a couple of things here. So first we need to get that variance to a standard deviation here, or maybe we want to get the standard deviation to a variance. So what if we just say we've got r times, and we want 1 over sx here because that'll give us the variance in the denominator. And let's write this out more clearly for a second. Then we want to get rid of that standard deviation in the numerator here. So what we end up with here is we just get that beta 1 is equal to r times the standard deviation of y over the standard deviation of x, which is the conventional formula. So that concludes the proof. Thanks everyone for watching.